Okay, so when we put an acid and a base together, they're going to go through a reaction called a neutralization reaction, and that is going to, if we have a strong acid and a strong base, this is the good old honors chemistry, it makes us salt and water. And if you don't know that, I'm about to tell you, but hopefully that was in your head already. Anyway, if I have a strong acid and a strong base, of course the reaction will go to completion, but even if I just have a strong acid and a weak base, or a strong base and a weak acid, as long as one of them is strong, it will continue to go to completion, and the KQ will be greater than 1. So that's cool, right? So again, strong acids, we already talked about those, and bases, we talked about how they completely dissociate, which means in water they completely ionize. All the particles will break into their ions. Okay. Hydrogen and hydroxide ions are going to form water, obviously. And then, so here's the thing. Check this out. The KQ for hydrogen and hydroxide forming water, this is what we had talked about during the do now. If I reverse this reaction and run it this way, hydroxide and, if I just do hydrogen, it's the same, right? If I reverse the reaction and write it this way, well, guess what happens to the KW? It's now, if I reverse the reaction, I have to take the reciprocal of it, which is 1 over 1 times 10 to the negative 14th. That means the K, the equilibrium constant for this reaction is 1 times 10 to the positive 14th. This reaction is very favorable, right? At equilibrium, I want to make, this is going to make water. So if I have any hydrogens present, even if the hydrogen is stuck to fluorine, and I have hydrofluoric acid, or if the hydrogen is stuck to cyanide and I have hydrocyanic acid, those are both weak acids. If there is a hydroxide present in solution, this will go to completion. The hydroxide will be able to go to the weak acid and take its hydrogen and make water, because this reaction is very favorable. How do you feel? So you don't have to have two strong. You can have one strong, one weak. As long as one of them is strong, they'll go to completion. All right, and so what ends up happening is we can do a neat little BCA table and get our moles, and if we have a certain amount of acid and a certain amount of base, we can do just a normal reaction, and we can put the moles in and subtract X plus X, all that, right? And then we can, whichever one we have left with, if we have extra hydrogens, it's going to be acidic. We can take the pH. If we have extra hydroxides, we can take the POH and then subtract them from 14. That's kind of where we're going. How do you feel? It's not too bad today. All right, so let's look at an example. When I graded y'all's test, which, oops, that's the wrong button. On Unit 1, we had talked about net ionic equations, and I graded your test because that's my job. And I still remember to this day how poorly you did on writing net ionic equations. So you can just be like, I know this stuff. No, you don't. I graded your papers, okay? So if you feel good about this, fine. But I highly recommend that you write the full equation and then write the net ionic, which is what I'm going to do. Thank you. Anyway, we have 250 milliliters of 0.35 molar hydrochloric acid, and that's a strong acid, right? And your head just be like, okay, that's completely dissociating. With 150 milliliters of 0.5 molar sodium hydroxide. Write a net ionic equation for this reaction and find the pH of the final solution. So here's the deal. These are not equal molar, as in I can already eyeball this and tell you that I don't have the same amount of H's as I do OH's. So I'm going to have to do some math, and when it's like this, you should do a BCA table. But the first thing we need to do before we write the BCA table, I guess we need to write the reaction, because that's what's at the top of the table, right? So let's go ahead and do that. I'm going to write the full equation. I have hydrochloric acid, that's going to be aqueous, and then sodium hydroxide, which is also going to be aqueous, and a strong acid and a strong base, when they react, it will form water, and a salt, and the salt is sodium chloride, and the sodium chloride is aqueous. So when you're writing net ionic equations, if something goes into the reaction fully dissociated and aqueous, and it comes out fully dissociated and aqueous, that means it went to the party and didn't dance with anybody. Nothing happened. It didn't involve itself in the reaction. So there are 2 spectator ions in this reaction. Which 2 ions didn't do anything? They didn't make a product, and they were dissociated the whole time. Jonathan, what's the spectator ions?
Hydrogen.
made one substance. What did we make? Made water, right? So what it went into making water? The hydrogen and the hydroxide. So those go into the net ionic equation. They actually were involved in the reaction. As soon as I put the hydrochloric acid in water, it breaks up into hydrogen and chloride, right? So the chloride didn't do anything. And over here, the chloride is still floating around in the beaker, still not doing anything. Same thing with the sodium. Breaks up, doesn't do anything. So the net ionic, I'm actually going to leave out the spectator ions of sodium and chloride. Okay, so the net ionic looks like this. And how does that make you feel? Ring a bell now, it's been a minute, right? So again, an easy way to think about it is if something goes in aqueous and fully dissociated, and then comes out aqueous and fully dissociated, that will be the sodium chloride, then those are your spectators, and they don't need to go in your net ionic equation, okay? So we've not really done anything yet. It said to find the pH of the final solution. So what we're going to do, this is the reaction right here. And what we're going to do is we're going to make a BCA table, and we're going to calculate the moles of hydrogen. We're going to calculate the moles of hydroxide. We're going to put them into the table, and we're going to go through the reaction, and we're going to see which one's left, hydrogen and hydroxide, and then we'll be able to calculate pH. So some of you guys are probably thinking, well, I can do this in my head, blah, blah, blah. No, do what I'm telling you, please. Because it gets worse. If you think this is it and we've arrived, you're wrong. We're about 1/3 through the way of this unit. So here is the total ionic equation, and then there's the net. See how the chloride and the sodium did not do anything. They were spectators. All right, so what I'm going to do here, you can do a bunch of stoichiometry and find the limiting reactant and all that, but we never did stoichiometry to find the limiting reactant. We always use BCA tables, and this is why I made you do that 3 months ago. And so I'm going to go ahead and I'm just going to like make this go away. And I'm going to write my net ionic equation at the top. And I don't really have a lot of room to be able to write and fill in this BCA table. Can I put like molarity in here? No. So what I have to do is I have to find moles. So go ahead, you can calculate moles of hydrogen and moles of hydroxide, can you not? And so you should do that right now, and I'll do it too. So 250.35. So I have 0.250 liters of hydrochloric acid, and the molarity is 0.35, so that means I have 0.35 moles in 1 liter. Watch what I'm about to do right here. And so you may feel like, okay, I'm just going to multiply those together, and I'm going to get an answer, and that'll be my moles of hydrogen. And you'd be right, except that you would not be right. So check this out. I don't know how many seconds this is about to take. I think it's about 2.5, and it's totally worth your time. 1 mole of HCl for every 1 mole of hydrogen. That net ionic equation, did it have HCl or did it have hydrogen? Not every reaction we're going to do is 1-to-1 ratio. So if we were doing an acid-base titration, which you don't even know what that is yet, but let's just say we were using calcium hydroxide. If you do this and you're just like moles, blah, 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 you're going to mess up because there's 2 hydroxide in every calcium hydroxide. You understand? So take the time to make sure you're ending with what you're really looking for. I know this didn't do anything mathematically, but I've seen enough papers that look like a hot mess because people were lazy. So do this. Anyway, I feel like that was 0.08 something. I got a calculator. Alright, great. 0.0875, and that's moles of hydrogen, and now I feel all happy inside because that hydrogen is what my ice table, or excuse me, a BCA table says. On the other one, it was, so I have basically 150 milliliters of 0.5 molar sodium hydroxide. And notice I'm going to take the time to say 1 mole sodium hydroxide is 1 mole of OH. How you feeling? All right, so now we're going to put these numbers into our ICE table, our BCA table. Oops. Were those the right numbers, or did I mix them up?
Oh, that's right.
Okay, cool. So, and then of course this is 0 at the beginning. This is minus x. Remember, the smallest x value is your limiting reactant because that's actually the one that's going to run out first, right? So that means that x is equal to 0.0750. If you don't think about it, or you don't feel like thinking at all, if you just pick this one, you'll see that when you put it in over here, you get a negative number, and you're like, oh, that's wrong. Okay. So x is equal to 0.0750. And so I'm going to run out of hydroxide. It's going to be completely used, so it's my limiting reactant. And so here, when I subtract that, I'm left with 0.0125 moles of hydrogen. And then I make, just for fun, that's how many moles of water I make. But that doesn't affect anything. Now, it wants me to solve for pH. Is this pH is a negative log of hydrogen ion concentration. Is it the hydrogen ion concentration, though? No, so this is moles. If you take this and put it into the pH formula, you're not going to get the right answer. So what we have to do at this point is kind of like what we did, I think, on acid base 1, where you took just the moles of hydrogen, and then we're going to divide that by the total solution's volume. So that's going to be 400 milliliters, right, if I add these up. And so I have, 0.400 liters. And when I divide, I'll get my molarity of hydrogen, and then I can use that in the pH formula. So that's my concentration of hydrogen. And the negative log of that answer is the pH. And so I find the pH to be 1.5. And it's got 2 sig-figs, so it's really 1.51. Are you okay? Now, when y'all make your little video and you have your answer key, they don't make a BCA table. They just do a few stoichiometry problems and they just keep doing them. You can do it that way. That's fine. But I don't like to show you that because it's cool while you're doing it, but it just all kind of meshes together and you don't know what you're doing, really. That's what I have found to be true. That's what happened last year to your friends. It didn't work out well. And then we had to relearn everything. So hopefully, I don't think either way is faster or has more or less work. I just feel like when you're done with the BCA table, you have more information and it's laid out for you that you can see what the heck happened. But this is how they do it. I mean, they're doing several little math problems. They rounded off throughout here, which you're not supposed to do that really. But since they rounded off, they got a pH a little bit lower, but same idea. All right. So moving on. So what I was saying before is that last reaction, strong acid, strong base, it makes water and a salt. If you have a weak acid and a strong base, it's still going to go through to completion. Each hydroxide, even, it's going to dissociate. It's going to be able to take that hydrogen ion off of that weak acid. So it's going to be able to remove it because of its strength as a base. It's a strong base, right? So it's a strong hydrogen acceptor, and so it's going to accept the hydrogen off the acid. So anyway, these aren't any math to them, not yet. If I take that's nitrous acid. If you don't know your polyatomic ions, you're about to have a problem, right? Because that's not nitric acid. This is a weak acid, right? So nitrous acid and potassium hydroxide. We're going to write the net ionic equation and identify the aqueous species that have the highest concentration at equilibrium. So I think, again, check this out. I have the same concentrations. So I'm going to just be able to write the equation and look at it. If you have different concentrations, then it would be a good idea to make an ice table, and we'll do that. Okay, but right now it's all equal. So let's go ahead and write the full equation. I have nitrous acid, and that's aqueous. And then potassium hydroxide, which is also aqueous. And that's going to give me still water. And it is going to produce a salt. And the salt would be potassium nitrate. Okay, now here's the deal. Before I go to make the net ionic equation, if I have a weak acid or a weak base, that HNO2, when I put that in water, does it completely dissociate? So I cannot just write H plus for that. I can't, because it's not just H plus in the water. So if a weak acid or weak base, you have to write the whole thing in the net ionic. Okay? Having said that, this whole little molecule is mostly hanging out in the water, right? As a whole thing. So when I write the net ionic, I do have to include that whole thing. I cannot break it up into the hydrogen ion. Now, on the potassium hydroxide, is there a spectator ion with that? The potassium. The potassium does nothing at any point. It completely dissolves in the water and it ends up floating around the water. It didn't do anything. It didn't help make the product, nothing. So the net ionic, I'm just going to have hydroxide here. The water's still a thing. I mean, that's important. It was made from the reaction. And then over here, I'm going to have the nitrite. Okay? The nitrite is a conjugate base of a weak acid. So that's important to us right now for two reasons. I don't remember the first reason. The second reason, the important reason is you realize this is making mostly water, right? And with the NO2. The NO2 minus, because it's a base and it's a strong base because HNO2 is a weak acid, this solution, even after it's gone to completion, will not be a pH of 7. Hydrochloric acid and sodium hydroxide make a pH of 7 when you're done. Because you just have water and those weak conjugate acids and bases, right? Well, with this, the pH of this solution when I finish will be greater than 7. That's a huge thing that they ask about in the AP exam, okay? So, anyway, having said that, what is most prevalent at equilibrium? Well, the aqueous species that I have at equilibrium would be the potassium, right? Even though it's not in the net ionic, it would still be 1 molar concentration. And then I would have the nitrite. The hydroxide, I'm not going to have any more hydroxide. It all went into making water. Okay, so I'm just going to have the nitrite and the potassium. How you feel? Alrighty. Cool. So that's what I had just said right there. So on this one, let me make sure this was, yeah. Go ahead and try to write the net ionic equation for this one and see if you can figure out the highest concentrations at equilibrium by yourself. Everybody here today? Okay. Because water isn't aqueous, because water is water. Water is the reason this is happening. But yeah, that's a good question. But if it was a solid or a liquid, it wouldn't be. It has to be a aqueous deal. equation or reaction, when I go to write the net ionic equation, phosphoric acid is a weak acid. And the reason it's a weak acid is because it's less electronegative than something like sulfur for sulfuric acid or chlorine for like perchloric acid or something, okay? So I'm going to include the whole thing there. So there it is, right? And then as far as this, the sodium is the spectator ion, right? And so I'm going to have hydroxide. And then I'm certainly going to have the water because it was formed during the reaction. And then here, be careful. If I were to ask you to write hydrochloric acid and break it up in water, you wouldn't think twice about putting a negative sign on the chlorine because it accepted an electron from the hydrogen. But you may have forgotten to put the negative sign here. Be careful. A good way to check yourself is that your charges should balance. And what I mean by that is, on the reactant side, I have a minus sign, so on the product side, I better have a minus sign too. See what I mean? Did anybody forget the minus sign? No? Well, good for you. And so the species that have the highest concentration at equilibrium, that would be the sodium ion and then the H2PO4. All the hydroxide is going to be used up because I have equal molar concentrations of these. So every bit of this, if you can see an ice table in your head, this is minus X, that's minus X, X is 1. They're both all gone, right? So all I have is products left. On the next one, that's not the case. How you feeling? Good? This isn't too much math, so this is just getting ready for more math. This is math getting you ready for more math. Okay, cool. All right, now this one is, let me make sure they're doing it the same way. Yeah. I don't really like how they took two hydrogens in the same reaction. That's not right, and I don't like it, so I'm gonna skip this one. I'm skipping this one too. Not because I don't want to, just because we don't need to do it. So if I have weak bases, if I have a strong acid, it's going to go to completion just like on that last one. So a lot of times weak bases may have nitrogen. If like ammonia, if ammonia is in water, right, you know, it's going to form a hydroxide, but it doesn't actually carry a hydroxide. Okay, so here we go. If I have equal volumes of ammonia and hydroiodic acid, which is a strong acid, if I mix them, do you think you can handle writing the net ionic equation for this? You can do it? Do you have a question?
Yeah.
What? I think you're. Where are you on the last line? Yeah, the one.
Yeah, it's only one round.
So here's the thing: if it's not one of those 8, then it's a weak base comparably. And so really, when we're talking about strong and weak, there's like medium. So for example, like acetic acid is medium strength really. But if it's not one of those 8, it's not a strong base as far as that goes. So like that slide where it's talking about like the conjugate base of a weak acid, that would be like the fluoride ion. The fluoride ion is a strong base comparably, but stronger than water. But it's not going to be one of the 8. Do you understand?
So, like, just in relativity to the equation, you could consider it a strong base or a strong acid?
Yes, in terms of the reaction that went through. Let me show you what we're talking about. Let me just go back to that slide. So if we do that, if we say, you know, HF, which is a weak acid, plus, I don't know, a strong base. Wait. We have to go the other way with that. There's a hydrogen involved in that too. I'm trying to think of a cut and dry example of what you want me to do. Because it's going to be, there's like that one reaction that's there, and then there's another one that's understood to be there, and I don't want to confuse everybody. But do you understand what I'm saying?
Mm-hmm.
Okay. If it's not one of those 8, it's not going to completely dissociate.
So you just be like a stronger base in terms of that reaction.
Mm-hmm. in comparison to the rest of the reaction. If it was one of the 8, then we wouldn't even be on the slide. It would be what we just did with the actual strong bases. All right, so on this one, do you think you can give this one a whirl as far as writing the net ionic equation? I bet you can. It's equal molar, so we're good there. Do you want to try? So sad, you guys. Y'all almost look bored sometimes. In second period, everybody's just like. You can give it a whirl if you want to. I'll give you a little head start. I'm gonna write the whole thing. Is that what you got? Yeah. So, you can choose to have written this as NH3 plus hydronium, H3O, but if you did that, you would have to write water over here. So, up to you. But notice my charges, they are equal. I have a +1 charge on both sides, and all my elements are balanced as well. So I think they chose, they chose to do that. They chose to write out hydronium, which is fine. But if you do that, you make sure that water's showing. I don't think that was necessary. And it's my preference to always just use hydrogen because on your formula sheet it has hydrogen. So anyway, so the iodide and the ammonium, they will have equal concentrations because they came in with equal concentrations. So there's that. We don't really need to do this. Just carbonic acid in water, it dissociates immediately, and the carbonate ion is a base. The AP exam doesn't require you to know those things anymore, but it's just, something good to know. That's why ocean acidification is a problem, because calcium carbonate is what seashells are made out of, and so the ocean is using seashells as an antacid, as carbon dioxide, which is carbonic acid, that when it dissolves, makes the ocean more acidic. Unless climate change isn't a thing, I can't remember.
Yeah, definitely.
There we go. All right, so y'all are funny. On this one, I think I was going to skip this one. And we don't have to talk about weak acid, weak base. That's not a thing for our class. We don't have to do that. We don't have to calculate the pH of that. We don't need to do it. It's not important. So moving on. This part here, y'all understand that ammonium is, don't read all this, don't freak out. Do you know that ammonium is the conjugate acid of ammonia, which is a weak base? So guess what? If I have NH4 in water, the solution is going to be acidic. Okay, you follow me there? Don't worry about all this. They're making this part too complicated. I'm not into it. So anyway, that's what I was just saying. So if you take NH4, so if I take ammonium nitrate, nitrate is the conjugate base of a strong acid. Nitrate is not going to do anything to a pH of water. This will. So if I put this in water, this is on AP exam, they'll be like, student adds ammonium nitrate to water, what will happen to the pH? You would have to know that it would go down, because this isn't going to do anything to the pH, and this will acidify because it's the conjugate acid of a weak base. It's not that hard, right, if you have them memorized. You good? Soaking it in, wheels are turning. There's a lot of practice on this on your homework, so it'll be good for you. All right, so check this out. This looks craziness. It's fine. What about, what about iron? This is too much. This is too much. This is also too much. hydroxide. Right? Can I act like I didn't do that? Can I just, don't look. Avert your eyes. I'm going to go home. I'm embarrassed by myself. There. Is iron 3 hydroxide a strong acid, or excuse me, a strong base? Is it one of those 8? So let's just say, now that wouldn't be given to you in the problem, but what if I had iron 3 chloride, and I put that in water? Is the chlorine going to do anything? No, because it's the conjugate base of a strong acid. What's the iron going to do? To the pH. Wouldn't it drop it because it's the conjugate acid of a weak base? See? This is fun. Super fun. You know what? It's more fun than what this says. I'm just making it much simpler. All right, so moving on. That doesn't matter for us. So again, here's my strong acids, right? The conjugate bases of strong acids. So if I have something that has chloride, perchlorate, iodide, nitrate, bromide, or bisulfate, if that is put into water or is with something else and put in the water, they are not going to affect pH. This doesn't seem like a big deal, but it is a super big deal. Okay. But if I add something like, see how, check this out, I have sodium acetate. Acetate is the conjugate base of a weak acid. So if this dissolves, it's going to make acetate in the water. So that is going to increase the pH because acetate is the conjugate base of a weak acid. So it's strong. Strong base raises pH. You get it? Courtney, you good? You're not giving me a good look. Yeah. Alright, cool. Let me go away from this. This looks like a hot mess. Are you with me that this is acetic acid? It's a weak acid, right? Its conjugate base is this, acetate. Do you get that this would be a strong base? And if I was to just put this in water, it would raise the pH of water. Well, what if I had something like sodium acetate? This ain't going to do anything because it is the conjugate acid of sodium hydroxide. So it will not affect pH. So in the water floating around, that's not going to do anything. Sodium plus ain't going to do anything. This will raise the pH of the water. Now you good?
So it's like a general rule, strong base will raise the pH.
Yeah.
Okay.
Yeah, for sure. So bases raise the pH, absolutely. So there's that. I've written way too much to make this look scary, but it's not scary. You're about to do a lot of practice on this. We don't need to do that. We don't need to do that. We don't need to do that. We're good. Okay, so on your homework, I'm about to let you record it. Your answers anyway. You're going to do 1 through 16, but you can skip 4, 8, 9, and 12. 4, 8, 9, and 12, okay? You ready? Alright, here we go. So on number 1, they're not doing an ice table, but you should, because I know that you know better than this. Okay? Seen your work. It's not that great if you don't keep it straight, right? If you do a table, you'll feel much better about yourself. The reason we're skipping number 4 is only 1 hydrogen reacts at a time. This makes me sad and want to throw my computer. Moving on. Again, with that, no. Only 1 at a time. That's why I'm getting you to skip that one. We're skipping 9. On number 10, they're really trying way too hard on this. Sodium fluoride. Fluoride is the conjugate base of a weak acid, so it will raise the pH because it's a strong base. They're over here writing all this craziness. Just dissolve it in the water. Don't do this. Don't make it too hard. They're trying too hard, okay? So, anyway. So please don't write so much, okay? Thank you. Good time. make sure as you do this, you do get the concept, because as we start with with titrations, we're going to be combining acids and bases, and then it's going to be like, well, what's the pH, blah, 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 blah. If you don't know this whole little salt, anion, conjugate base, conjugate acid, blah, 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 you're not going to do well. All right, so these are really good practice. They're concept based. Y'all didn't ask, did y'all have any questions about the homework from acid base 1 or 2? Yes, ma'am.
I had a question about, number 4.
Why